Hi there. In this video, we're going to do some practice with constructing and interpreting confidence intervals for a proportion. And these are the theoretical confidence intervals in this section. Okay, so I've got, as a reminder, a bunch of notes for you here at the top, okay? So remember, in order to do this, we do need the conditions to be met for the central limit theorem. Otherwise, when we use our z star, we're not capturing the middle 99% or 95% or whatever our confidence level is if we don't have the right shape, right? So we do need these conditions to be met, and I'm going to do kind of a quick check of the condition. So just read whatever assignment you're doing, read whether it's asking you to do like a full write-out of all the conditions, or if you can just kind of quickly check them off and which one they are, okay? I would normally only have you do like one full write-out per assignment or quiz or test, not for every single question, okay? Because we need to do it for sampling distribution questions, we need to do it for confidence interval questions, and we'll need to do it for hypothesis testing questions as well, whenever we're using the theoretical method, okay? So let's review. It's also good review and good practice, right? So the conditions are, and remember, this is coming from our back-end sampling distributions, our conditions and models sheet, where we have all the conditions and the models that we're using for the sampling distributions, right? Okay, so independence, the subjects need to be independent of each other in terms of the variable in question. We need to have a random sample. We need to be sampling from a large population. So our population needs to be 10 times our sample size. And then the success failure condition. So n times p hat and n times q hat both need to be greater than or equal to 10. And that's to make sure we have a big enough sample size relative to p to have our normal distribution, okay? And then I've repeated the formula here, same one we were just using. And then we're going to write out our interpretation, which we've done in the past, but just good review. In our interpretation, we'll write our confidence level, the interval, and then we'll include the context, the wording for the population proportion. So this is context or variable, whichever way you want to think of it. Any units, in this case our units would be percentage. Okay, so let's do an example. Okay, I keep this box up here. A 2012 poll asked 166 adults whether they were baseball fans. 46% said they were. Construct and interpret a 95% confidence interval for the true proportion of U.S. adults that are baseball fans. Okay, let's say this is the Baseball Association, or somebody wants to know how many people, what proportion of U.S. adults are baseball fans. Are you a baseball fan? It says also state the standard error and the margin of error. Okay, this is just good practice. Also state the standard error and the margin of error. Okay, so we'll do that as we go. Okay, so first conditions, and if it helps, I'm going to kind of do this in 3 columns, just like the notes are up above in 3 columns with the conditions, then the interval, then the interpretation. But if you want to write it out in a different way, that's fine too. Okay, so independence. Okay, so we must, the people must be independent of each other in terms of whether they're fans or not, baseball fans. Okay, so we couldn't survey a baseball club, right? Or an intramural league, because people would be more likely to be sports fans, right? So subjects must be independent in baseball, what would you call that? Baseball liking, baseball preference. Okay, then we need a random sample. Okay, that's all I have to do for that one. Then large population. Okay, we have a fairly small sample size here, 166. So we need, put a 0 on there, we need our population to be 10 times that, 1,660. Okay, I think our U.S. population is safely much larger than that. So our population is larger than 1660, and I'll just write times 10 up there. Okay, and then success failure, we're just going to check this real quickly. 166 times our p hat is 0.46, and 0.166 times, I'll figure out what 1 minus 0.46 is. Okay, 54, that makes sense. 46 and 54. 0.54. This is pretty close to the middle, so it shouldn't be a problem, right? Remember, it's when you're in the very high or very low percentages that it's more of an issue. 166 times 0.46. Oops, I calculator typo. 166. I want to put an arrow there because that looks like I wrote a decimal on the notes because I was doing a bullet point. 166 times 0.46 is 76.36. And then 166 times 0.54 is 89.64. So these are both greater than or equal to 10. So I'll just put a little check mark there. Okay, so there's our conditions. And then I'm going to put my formula in the middle, p hat plus or minus z star square root p hat q hat over n. So I wrote my formula in the middle. Now I'm going to plug in the numbers. So this 46, we've already used it. And what's kind of nice is when you're doing the conditions, you calculate q hat. We didn't have to. We could have done 1 minus 0.46. But now that I know it, I can just put it in my formula if I want to. So I'm going to go 0.46 plus or minus. This is 95% confidence. So remember that corresponds to a z star of 1.96. I'm going to use 1.96. I always remember that because it's approximately 2, right? But it's more exact. It's 1.96 times the square root of 0.46 times 0.54 over 166. Okay, I'm going to do 0.46 plus or minus, and then I'm going to calculate this whole margin of error at the same time like we did before. So let's put it all in at the same time. 1.96 times the square root, and I might not even need, probably don't even need that time symbol actually. It'll imply that's multiplication. Times the square root of 0.46 times 0.54, or remember you can do the parentheses 1 minus 0.46, divided by 166. Okay, and this is giving me, okay, 0.0578 plus or minus 7 to 8%. Now that makes sense to me because it's such a small sample size. So also when you have a small sample size, you don't have as much precision. So it's going to be a wider interval. So good thing to double check. If I got like, 50%, then I'd be like, something's off. That can't be that wide. Okay, so now I'm going to write my two numbers in my interval. I'm going to go ahead and subtract and add in the calculator. So 0.46 minus 0.0758 is 0.3842, comma 0.46 plus 0.0758, 0.5358. So that's our confidence interval. Okay. And if you prefer, you can write it out in percentage. We might want to do percentage for our interpretation. So I'm going to round this a little bit too. I'm going to do 38.4% to 53.6%. Okay, what we're doing is all approximate anyways, and I think it's also easier for people to conceptualize when there's fewer decimal places. So, for example, in that marijuana study, they rounded it to a whole percentage, even though we know there was probably a decimal on there. So we also could have done 38% to 55%, or sorry, 54% if I round that one up. So either way is fine. In My Open Math, it's more particular about the decimal places. So look for each question how many decimal places it's asking for there. Okay, now remember way back when we interpreted our confidence intervals? It's been a while, but the interpretation is exactly the same. It's just that our method of calculation was different. The theoretical one versus the bootstrap one with 2 standard errors, or the bootstrap one with percentiles. Okay, so our interpretation is something like, we are 95% confident that the true proportion or population proportion of, it doesn't specifically say US, but I'm just going to say adults. So I'm looking for what's the population, right? Because in order to get my parameter in there, I need to interpret the population. The true proportion of adults, and I could also read what it asks for the interval for, right? That's the other, should be the same. Interval for the true proportion of US adults. Oh, there it says US adults that are baseball fans. So we're 95% confident that the true proportion of adults, or US adults, that are baseball fans is between 38.4% and 53.6%. Okay, so that is a confidence interval example. And this is a little bit longer on the conditions, so I'll do a little bit shorter on the conditions on this next one. Let's do one more example, and if you'd like to, if you feel ready, try it yourself. Pause the video, try it, and then come back. Or I'll keep going and we'll do it together. Okay, so let's see what this one says. A 2016 Gallup poll asked 1,021 U.S. adults whether they were satisfied with their current health care. Okay, 581 people said they were satisfied. Write and interpret a 99% confidence interval for the true proportion of U.S. adults who are satisfied with their health care. Okay, it's unclear whether this is health care, like the care they're receiving from the doctors. Actually, if I read it that way, it's not surprising. I was first reading it as their health care coverage or insurance coverage and cost and all that. That I would think would be lower. So maybe it's the health care they're receiving. Unfortunately, I'm not quite sure. I wish we could look for this study and see if we can get more information on it. Okay, so we do have our N. And we have, okay, so this is great because in the first example, they gave us the p-hat. They gave us a p-hat in a percentage, right? We didn't have to do anything there. But sometimes they're going to give us the number of people, and we have to find p-hat ourselves, okay? So this time we're going to find p-hat, and we've seen that before, but it's good practice. Okay, so I'll do a little bit more brief on the conditions, which you can do if it doesn't say, like, write out or describe each condition. So I'm just going to write independence, check, random sample, check, large population, I'm still going to do 10 times. I'm going to say population greater than or equal to 10210, right? 10 times. So we're adding a 0 on the end. So that would be 10,200. So U.S. adults is way larger than 10,200. No problem there. We are going to do the success failure though. Okay, so success failure. We have 1,021 times p hat. Okay, so I'm going to actually have to find my p hat first. I'll go over into the middle section here because we're going to need to do that. Our p hat is 581 over 1,021. Okay, so let's calculate that. 581 divided by 1,021 is 0.5690, and there's a 4 after, so 0.5690 or 0.569. I am in general going to keep p hat to 4 decimal places. It turns out the fourth one was a 0 in this case. And that way it'll match up with our, do our standard error to 4. That way our calculations are precise. We can always round to fewer digits later on if we need to. Okay, so now that I know my p hat, I can multiply. It's also in the middle, so I'm not worried that this is going to meet. 0.569 and 1,021 times 1 minus 0.569. I'll do it the other way this time. 1,021 times 0.569 and 1,021 parentheses 1 minus 0.569. Okay, so 5, and you can round these as well if you want to. So 581 and 440. I'll change it to approximately equal. Those are both greater than 10. No problem. Okay, great. So now let's go ahead and do our interval. So our p hat, I'm going to shift this over a little bit. I'm going to write my formula, p hat plus or minus z star. Oh, that's right. We got to think about our confidence level. Times the square root of p hat q hat over n. Okay, let's plug everything in. Our p hat is 0.569 plus or minus z star. So I've got my last notes page here. We're doing 99% confidence. So this is 2.5758. 2.5758 times the square root. Another thing to look out for in the MyOpenMath is look for how many digits it wants the z star to. Sometimes it'll tell you to use fewer digits here, and then you would round it like 2.576. Sometimes you see that. It's only to 3 places. It's just for the automatic grade. It makes a difference in the final answer. Okay, our p hat is 0.569 in the square root, and I never calculated q hat. You're welcome to put that in if you did. I'm just going to put 1 minus 0.569. Okay, so you have an example with it each way over 1021, 1021. Okay, I'm saving some room at the bottom to do my interpretation because I've kind of gone over into my right column with these large numbers. Okay, so now I'm going to write 0.569 plus or minus and do the whole margin of error all at once. Okay, so 2.5758, that's our z star, times the square root of 0.569, parentheses 1 minus 0.569. Close parentheses, divided by, but still in the square root, 1021. So that's plus or minus 0.0399. Okay, so pretty much 4%, right? That looks much better. That's a more reasonable interval than plus or minus almost 8% from the other one, right? And that's because we had a bigger sample size, 1021. Okay, so now I'm going to write I'm going to go ahead and add and subtract to get our interval. 0.569 minus 0.0399 and 0.569 plus 0.0399. Okay, so we have 0.5291 comma 0.6089. Or if I do percentages and round it, now we'll have 52.9% to 60.9%. Okay, it seems like the narrower the interval, the more important maybe having a decimal place is, right? Because, I mean, this is still would be 53 to 61. But if you were getting a really narrow interval, then you might want to keep it more precise, right? Okay, so now we can write out our interpretation. And from up above the notes, remember the three things are the confidence level, the interval, and the wording for the population proportion. Okay, so I'm going to use a similar wording. We are, or we can be 99% confident that, okay, this time I'll put the percentages first. I'll vary it just a little bit. That 52.9% to 60.9% of, okay, now this is where I need my population, right? And I'm going to emphasize that it's a population by saying all U.S. adults. Because we're not talking about the sample. We know the sample is 56.9%. We don't need to put a range around that. It's now that we're inferring to the population, that's why we need the plus or minus for sample to sample variation. So we're 99% confident that 52.9 to, oh, those are both 0.9s. Okay, to 60.9% of all U.S. adults, and what were they surveying? Were satisfied with their current health care. Were or are satisfied with their current health care. Okay. Great. Well, I hope that helps give you another example, and I will see you in the next video.